Hi, I'm going to review the Chapter 11 material with you about simplifying radicals and solving radical equations. So in these first three examples, what we're going to do is simplify these expressions, and we're going to also extract all the perfect squares from each of these radicals and then leave our answer in radical form. So if you remember, we have to have the same index and the inside of it, the radicand. They have to be the same on all three of this if we want to combine all three. And once they are, you're going to take the coefficients, which for this one, there's an invisible 1 out here. And all you're going to do is combine the coefficients. So 2 minus 16 is negative 14, and negative 14 plus the 1 would be negative 13. So I have negative 13 times the square root of x. And that's basically it. Again, all you're doing is keeping the actual radicand and the index the same, and you're just simplifying the coefficient on the outside. For this one, I would expect you guys to break apart the square root of 20 into two perfect squares. So the largest perfect square that goes into 20 is 4, and it does that a total of 5 times. The square root of 4 is 2. So I'm going to rewrite this expression as 2 radical 5. And then this 45 over here, I'm going to break this apart into the square root of 9 times the square root of 5. Now, the square root of 9 is 3, but I already have a 6 on the outside. So you would have to multiply the 6 on the outside by the square root of 9, and you would get 18. And then you would have a radical 5. So at the very end, now that we have the same radicals, I can combine the coefficients. 2 minus 18 is negative 16, and then again, you just bring the radical down with it. And then the last problem. This one has cubed roots in it, so we're going to simplify this expression first by extracting the perfect cubes, and I'm going to take out some of these variables. So first thing, the cubed root of 8 is 2, so that just comes right out. 3 goes into 3 one time, so m is to the first power. N, the 3 over here, goes into 5 one time, so I'm going to take out n to the first and be left with the cubed root of, since 3 went into 5 one time with a remainder of 2, I'm going to have n squared left. And then over here, 3 does not go into 2, so I cannot take out the letter m, but 3 goes into 4 one time, so I'm going to take out n, and be left with the cubed root of m squared times the 1 remainder that I had for n, which again was to the first power then, just because the remainder was 1. So at the very end, we have to look if we can go any further with these radicals, and it does not look like I can, since again we're adding these two quantities. You would need the index and the radicand to be the same. So since the radicand is not the same on both of these, this is as far as you can go. With this one, we are going to be multiplying now. So in this first one, like I said, we're going to multiply before we simplify. So 15 times 3 is 45. I have x to the 4th times x to the first power. The rule is that when you're multiplying two exponential expressions, you're going to add the base number, or add the exponents. So x to the 5th power then, and then y to the 5 plus 7, which is 12. So now we're going to, again, extract the perfect squares. So I'm going to look at what's the largest perfect square that goes into 45, which is 9, total of 5 times. So now I'm going to rewrite this as 3 times the square root of 5x to the 5th, y to the 12th. And now I'm going to take out, or we're going to extract out the perfect squares for our variables. So I need to see how many times my index here, which again the index is 2 since it's a square root. So 2 goes into 5 twice evenly, so that means I'm going to take out x squared and save a little room. On the inside, let's just fill out the remainder right away. If 2 goes into 5 twice evenly, that means I have a remainder of x to the first power. And then 2 goes into this 12 6 times evenly with no remainder on the y. So I can chop that off, and that is your final answer. And then for this problem, I have 4.2 times this cubed root. So I have a cubed root on the outside. So the first thing that we're going to have to do is multiply 4.2 times 3.4. And that comes out to 14.28 times the cubed root. And now I'm going to simplify the inside. I have 4 times negative 10, so negative 40. M to the 5 plus 2, so m to the 7th, and then n to the 3 plus 1, so 4. So now we're going to simplify this expression, same exact way, except now that we have a cubed root, I'm going to look at what's the largest perfect cube that goes into 40. And since we have a negative sign with the cubed root, I'm going to attach that negative sign to my perfect cube. And it's going to be negative 8 times 5 is what would give me 40. So the cubed root of negative 8 is negative 2, because negative 2 to the third power would give you this negative 8, so working backwards. The cubed root of negative 8 is negative 2, so I'm going to have to multiply it by this 14.28 on the outside. So I would get negative 28.56 times the cubed root of this 5, which was left over, and then the variables, m to the 7th, n to the 4th. And then our last step again is to take out or extract the exponents for the variables, the perfect cubes I should say. So leave the 28.56 out there. 3 goes into this 7 twice evenly, so m squared, with the remainder then of 1. So I'm going to have 5m to the first power left. And then 3 goes into 4 one time evenly, also with a remainder of 1. So this would be your final answer. And again, make sure to include the index on the outside of that radical to show me that it is a cubed root. So for these ones, we're going to solve these radical equations and then check for extraneous solutions. So for this one, I have a square root, which we're going to have to isolate the square root function. So I want to get this by itself first before we start squaring both sides. So I'm going to subtract 4, and I'm left with the square root of 2x minus 1 equals 6. And then what we're going to do is square both sides. And we're going to do this to get rid of the square root. So the square and the square root cancel each other out, and you are left with 2x minus 1 equals 6 squared, which is 36. So then you would add 1 to both sides and get 2x equals 37. And then the last step would be just to divide both sides by 2. So x would come out to 18.5. And what you would want to do again is check this answer by taking 18.5 and substituting it back in for x. So if I do that, 18.5 times 2 would give me 37 here. 37 minus 1 is 36 on the inside of the square root. The square root of 36 is 6. And then lastly, 6 plus the 4 would give me 10. So that answer does work out, which means 18.5 is my answer. For number 7, I have a cubed root on the right side. I also have this multiplier in front of the cubed root. So we're going to want to get rid of that 4 on both sides first. Like I said, it's a multiplier. So we get rid of it by dividing both sides by 4. So I end up with 3 equals the cubed root of x plus 2. So then what we're going to do to solve this is take both sides to the third power. So to get rid of a cubed, you have to take the cubed root. So on the left side, I have 3 times 3 times 3, which is 27. And on the right side, I have x plus 2, because again, the cube and the cubed root cancel each other out. So then my last step is just to subtract 2 on both sides. So I get x equals 25. And again, we'll check the answer real quick. If I substitute 25 in for x, 25 plus 2 is 27. The cubed root of 27 is 3, and then 4 times that 3 would give me my 12. So this answer also works out. So the next problem we're going to do then is to solve a radical equation that is going to have extraneous solutions. This one's going to be a little bit longer. So first thing that we're going to have to do here, again, is isolate the square root part of this, which means I'm going to have to subtract 3 on both sides. So I'll do that. So I'm going to have x minus 3 equals the square root of 30 minus 2x. And then again, we're going to have to square both sides to get rid of the square root. So this is going to turn this into a quadratic, actually. We're going to have x times 3, or I'm sorry, x minus 3 times x minus 3. And then the square and the square root here canceled out. So I do need to use a distributive property, which means I'm going to have x times x, so x squared. X times negative 3 is negative 3x. The inside is also going to give me negative 3x, and then negative 3 times negative 3 would be positive 9. So in order to solve a quadratic, you would have to first set the equation equal to 0. So first thing is to simplify this left side by combining the negative 3 and negative 3x. Now with the right side, what I'm going to do is bring over the 2x. Again, I want to set it equal to 0. So I have x squared minus 4x plus 9 equals 30. And then the last step to get it set equal to 0 is to subtract 30 on both sides. And we'll get x squared minus 4x minus 21 equals 0. And this expression down here, I'm going to copy it up here. And we are going to have to solve that using factoring, or you could use the quadratic formula. So I'm using, or looking for, my factors of negative 21. So two numbers that multiply to negative 21 that add up to negative 4. And those factors are going to come out to x minus 7 and x plus 3. So then we'll go through and solve these. So now that I figure out what my factors are, I'm going to set each one equal to 0. And solve. So I get x equals positive 7. And over here, x equals negative 3. So we need to take these two answers and substitute them back in to check our work. So I'm going to make a big box up here. I'm going to check my answers. So I'm going to substitute 7 in first to both sides of the original equation. And we're going to see if this ends up working out. 30 minus 2 times 7. So on the left side, I have 7 equals 3 plus the square root. And this is 30 minus 14, which is 16. So then 7 equals 3 plus the square root of 16, which is 4. And since 7 equals 7, that tells us that this first solution does work. Now I'm going to do the same thing with the negative 3, and we're going to try this. So I'm going to substitute it in for x in both of these values. And get 30 minus 2 times 3. 2 times negative 3, rather. So I get negative 3 equals 3 plus, and then the square root. Now this is 30 minus, and then this whole chunk here is going to come out to negative 6. So this is going to come out to 36. So you get negative 3 equals 3 plus the square root of 36 is 6. And at the very end, you have negative 3 equals 9. So that is not true, which means that this solution is an extraneous solution, and that 7 is really your only answer to this equation. And then here's an extra example, just if you want to try some practice yourselves. Both of your solutions will work for this. I am not going to write up the entire answer, but your x is going to come out to, looks like positive 5 and positive 2. If you try solving this, you will get these two answers, and then once you check them, both of them will work. So neither of those will be an extraneous solution. This next one, I'm going to be graphing a function and the transformation function. So I'm going to use my starting points here, 0, 0, 1, 1, and 4, 2. So I'll graph these. Again, the 0, 0 is what we call the initial point for this radical graph. I definitely counted the wrong there. Okay, so over 4 and up 2. Okay. So this is what a square root graph looks like. Now my transformation. So what's going on the inside for this g of x function is I have an x plus 3, which is going to shift it horizontally. It's going to translate it to the left 3 units. Our little rules was the opposite on the inside. This 2 in front of it is going to stretch my graph. It's called a dilation. So it's going to basically, it's a multiplier. It's going to multiply your y values. And then the minus 4 after the square root is going to be a vertical translation down 4 units. So I'm going to write down my 3 new points. And I'm going to subtract 3 from my x's. So 0 minus 3 is negative 3, and 1 minus 3 is negative 2, 4 minus 3 is 1. And then I'm going to multiply my y's by 2 and then subtract 4. So multiply this by 2 and then subtract 4. And now I'm going to plot these points for my transformed graph. So left 3, down 4. I have negative 2, and then 1, 0. So you can look at what this transform function looks like compared to the parent function. It is translated to the left 3 units, and it's translated down 4 units, and it's also a lot wider. It's twice the size, really, because the multiplier of 2. 2 left then, I believe. Oh no, there's like a few left. Okay. This next one, we're going to solve this equation for b. So what we want to do is find a way to get it out of the square root. So what I'm going to do is multiply both sides by 2. So I'm going to end up with 150 equals pi times the square root of 3b minus 1. And what I'm going to do is round this to the nearest tenth. So I'm going to take, I'll pull up my calculator here. Turn that off. Okay, so I'm going to take 150 and divide it by pi. And I'm going to round this to 2 decimal spots, so 47, or I'm sorry, to 1 decimal spot, so 47.7. And that is equal to the square root of 3b minus 1. And now what we want to do is get rid of the square root on both sides. So I'm going to square both sides of this equation. This is going to give me a pretty big number. So if I square 47.7, I'm going to take this number and multiply it by itself. And again, just keep rounding to the nearest tenth. So I'm going to get 2275.3 equals 3b minus 1. So now I'm going to move the 1 over to the other side by adding it. So I get 2276.3 equals 3b. And then your last step is to divide both sides of this equation by 3. So I'm going to get 2276.3 divided by 3. And you end up with a b value of 758.8. Oops. And again, you can check this answer by substituting it back into your original equation. If you substitute it in here for b, you would multiply it by 3, subtract 1, do this whole process, and you'd get something pretty darn close to 75. Since we rounded a few times, you're not going to get exactly 75, but I would just have you round to the nearest tenth. Next one. So we're going to simplify this by getting rid of the radical in the denominator. So if I want to cancel out the cubed root of x, you would need a cubed root to cancel out with x cubed down here, but we don't have that yet. So I need to multiply the bottom by the cubed root of x squared, and that would give me, enough x's on the inside to cancel out with this cubed root. So if I do it on the bottom, I have to also do it on the top. So on the top, I'm going to be left with 5 times the square root of x to the third times the cubed root of x squared. And on the denominator, I have 2 times this whole chunk here. Now again, the cubed root of x is going to, or the cubed root part will cancel out, and you're going to be left with just what's on the inside, which again would be 2x. So now I'm going to rewrite the top in exponential form. So I'm going to write this as 5, and then since there's a little invisible 2 on the outside, I'm going to write this as 5x to the 3 over 2 power. And then I'm going to write this one as x to the 2 over 3 power. And what we'll actually need to do is add the exponents. In order to do that, we'll have to find a common denominator. So I'm going to take care of that right now, and this will be in the next step. I'm going to write them with a common denominator of 6. So I would need to multiply 2 by 3 to get to 6. So I'll do the same thing to the top and multiply by 3 and get 9. And then over here, I would need to multiply 3 by 2 to get to 6. So I'm going to do the same thing to the top then. Multiply the 2 by 2 and get 4. So now I have this is my expression. And I'm going to go a step further now, and we're going to simplify these by adding them together. So I get 5x to the 13 over 6 all over 2x. And the madness still keeps going. The next thing is to write it in radical form instead of exponential form. So the 6 goes to the index of the equation. So 5 times the 6th root of x to the 13th power all over 2x. And then we need to see how many times 6 can evenly go into 13, which is twice. So I'm going to write this as 5x squared times the 6th root of x, because your remainder is 1. And all of that is over 2x. So I promise you this is the last step. Since I have an x squared on top and an x on the bottom, we are going to cancel out one of these x's. So you will be left with 5x times the 6th root of x all over 2. And again, this will be your final answer. Whoa. Okay, last problem is to figure out if two functions are inverses of each other. In order to do this, we're going to do a composition of functions. So I'm going to do f of g of x, which means I'm going to be taking the g of x function, which is the 1/3 x minus 3, or I'm sorry, minus a third, and we are going to be substituting this in for x in the f of x function. So this whole chunk right here is going to be substituted in for x. And again, what we're really looking for, if they are inverses of each other, is at the very end of this function, you would be left with just the letter x then. So I'm going to have 3 times the square root of 1/3 x minus 1/3, and that's squared, plus 2. So the square and the square root are going to cancel each other out, and you're going to be left with 3 times 1/3 x minus 1/3, and then the plus 2. So now you'll have to distribute a little bit, and I'll be left with, well, 3 times a third is just 1. So since I have an x there, the x will come with it. Minus 3 times this third is 1, plus 2. And at the very end, you are left with x plus 1. So since you do not have an x left over at the end all by itself, these are not inverses of each other. Okay, and that is the majority of the material that is on this test.